Okay, welcome back. We're at the whiteboard again because the book also doesn't have anything for this section. I mean, the book was mostly finished, not perfectly finished, which is fine. And anyway, I guess that just means we're at the whiteboard again. And we're talking about, this is chapter 15, which is called Separation of Variables. And separation of variables primarily as a method, put in parentheses, as a method of solving PDEs. And we'll talk about how we can at least guarantee. There are some PDEs that you can solve with separation of variables that won't fit our criteria today, but by and large, the criteria we give today is going to be the criteria that you would want to use something like separation of variables for if you're ever going to solve a PDE. So I'm going to talk about what the method actually is first, and we've been using it a little bit, and I was referring to it a little bit, but the method just comes down to the following. Assume u, which is our function we're trying to solve for as the PDE, assume that it equals a product of phi and psi in the variables that we're working with. I mean, if you're working with like 10 variables, you can have PDEs with as many independent variables as you want. You would assume that it's a product of 10 different variables. But today's kind of criterion won't apply in that case. Today's criterion applies in the case of 2 variables. Okay, so we're going to be the method for 2 independent variables, which are these classical cases that we've been approaching in class so far. So you assume that it's equal to the 2 of them, and then compute the PDE on this product. Rather than computing it on you compute it on the product and try to rearrange it to only functions of x on one side and only functions of t on the other side. Then this gives a system of 2 ODEs. So I think we're seeing this commonly in practice. How do we solve PDEs? We try to convert them to systems of ODEs. We have a much larger toolbox for ODEs than we do for PDEs, and because of that, if we can rephrase the problem in terms of an ODE, then we have a much easier way of solving it. So we gain a system of 2 ODEs, and in fact, it's not even hardly a system of ODEs for most cases of separation of variables. You just gain 2 ODEs and you solve them separately, and that's gonna solve your problem for you. But this only applies in a specific subset of PDEs. So let's describing the class of PDEs this will necessarily work for. We can describe the class as the following. If a PDE can be written as a sum, so this is jumping back to your summation notation that I know not very many of you liked a lot, but that's okay. So it's a sum of some functions. I'm going to index them by j of x against the derivatives in x. And if that's equal to a sum of functions of t and derivatives of t. And then perhaps you can also include just some generic function of x on this side. I don't think you can actually. Okay, so the sum of derivatives in x times possibly functions of x equals the sum of derivatives in t times possibly functions of t. Why are these useful? Why is this a useful class? PDEs. Well, let's consider these again. Heat equation. That's delta U equals partial t u. That's exactly in the above class, because the left-hand side is only derivatives of x, the right-hand side is only derivatives of t. The Laplace equation was, I'm going to rewrite it now as partial squared partial x squared u equals negative partial squared partial y squared u. Okay, well, I've replaced t with y in that case, but still, the two variables that I care about, all of them can be separated to the left for x, and all of them can be separated to the right for y. The wave equation, partial squared partial x squared u, even I can put a c squared in front of it, equals partial squared partial t squared of u. Everything is terms of x on the left and in terms of t on the right. And so this is kind of, in essence, this is why we were solving these with separation of variables. Because all of these really nice classical equations actually fall into this nice criterion where you can separate all derivatives and functions of x to the left-hand side, all derivatives and functions of t to the right-hand side. And it's not clear that the heat, Laplace, and wave equation were of that form right away. Right, we have to be a little bit clever as mathematicians and rearrange the equations and say, okay, can I, if I work hard enough, can I actually separate these? And you definitely can in each of those equations. So now we'll go on to examples, because I know we've had some practice with this, but let's actually run some examples and see maybe how we would do something like this in practice. So let's jump back to one of these situations of doing a separation of variables. We have maybe the x squared partial x partial squared partial x squared u plus partial t u equals 0. So this looks like it could be like our heat equation, and in fact it is kind of like the heat equation, but it's not 100%. It's like a modified heat equation because you have the x squared out front. And the x squared out front definitely modifies this away from where our heat equation has a solution. But this can definitely be written in the form, can be written as x squared partial x squared u equals negative partial t u. And so we have all functions of x on the left, all functions of t on the right, except for u itself. And so let's talk about maybe a step-by-step. Step 1, write u of xt equals phi of x psi of t, and plug in. And let's plug it into this kind of simplified version. If we do that, we get x squared, two derivatives, just gives me two derivatives in the x variable, psi t, and then I have negative one derivative in the t variable, psi prime t. Step 2 is always divide by phi x psi t. And that's going to give me, after some cancellation, gives me x squared phi double prime x divided by phi x, and then equals negative psi prime t over psi t. Step 3 is realize if left-hand side depends only on x and the right-hand side depends only on t, then both must be equal to the same constant, which we always call lambda. So they're both equal to the same constant lambda. Helps me out with step 4. Set each side equal to lambda separately. There's your separation of variables. So you set each side equal to lambda separately, and we have something like x squared phi double prime x over phi of x equals lambda, and we also have negative psi prime of t over psi of t equals lambda. And if we just multiply both sides by their denominators, we recover the following ODE. X squared phi double prime equals phi. And we recover phi prime t is negative lambda psi t. That was psi that I was talking about earlier. And those are just two separate ODEs. You might not have learned how to solve this first ODE on the left. I don't think you learned how to solve that one. There's a lambda there as well, right? Lambda. I don't think you've learned how to solve that sort of ODE quite yet, but it is a separable ODE, so you could potentially solve it if you wanted to. It's a second order separable ODE. That separable means something different than the current separation of variables separable. But definitely psi you know how to solve. So you know how to solve psi, and psi is e to the minus lambda t. You could always refer to Wolfram to get the solution to the other ODE, and if we do that, we recover that phi is c1 x2. I'll just call it a constant of lambda. Maybe I'll just call it c of lambda. It's a pretty ugly constant, but you can definitely solve for it. C2 x2, a second constant of lambda. So maybe call it c3 and c4, where those two depend on lambda, the powers, but the C1 and C2 up front do not. So after we have that, step 5 maybe, we'll call it step 5 is, let's fit it on the screen right over here. Step 5 is rewrite u of x and t, because it's just a product of the previous two. So we're just going to rewrite it as C1 x to the C3 of lambda plus C2 x to the C4 of lambda multiplied by e to the minus lambda t. And so we would find out that in this case, this is why it's a bit of a modified heat equation, right? Because we still have this exponential decay that the heat equation has, but that x squared out front is modifying these away from where we used to have cosines and sines. Now we have these x's to some power. And so that's where the modified heat equation is coming from. But that's maybe an example of separation of variables, and on the next lecture we'll go through quite a few more examples, so this will hopefully make a lot more sense by then. But that's kind of the overall procedure for separation of variables. So I'll see you in class. Bye.